Welcome to the Deep Dive. Today, we're going to be tackling a cosmic challenge, diving into some of those listener-submitted excerpts from Stephen Hawking's Brief History of Time.
Yeah.
It's a book that I think sparks a lot of curiosity,
Yeah.
but can be pretty daunting, wouldn't you say?
Oh, absolutely.
So our mission today is to make these complex concepts about the universe a little more accessible.
Right.
Pull out some of the surprising bits that'll maybe make you see the world,
Yeah.
or should I say the universe, in a whole new light.
It's definitely a journey through some pretty mind-bending ideas,
Right.
for sure.
Hawking starts by posing the big questions.
Yeah.
Where did the universe come from?
Mm-hmm.
How does time work? These are questions I think we've probably all pondered at some point, right?
Oh, yeah. I think everybody thinks about this stuff at some point.
What I find fascinating is how our understanding of these questions evolves over time.
Yeah.
You know, he uses this great analogy of an ancient belief that the Earth was flat.
Oh.
Balanced on a tower of tortoises, all the way down.
An infinite tower of tortoises.
An infinite tortoise tower.
Yeah.
It makes you smile a little bit, but it makes a good point.
It really does. Today, I mean, we know that idea is absurd. The Earth is a sphere. It orbits the sun.
Right.
But Hawking's point is that our current ideas about the universe right now might seem just as ridiculous to future generations as that tower of tortoises does to us.
Yeah, it makes you realize what we consider absolute truth now could be completely overturned by new discoveries in the future.
Absolutely.
What we think is impossible today might be common knowledge tomorrow.
Totally, yeah. And speaking of things that might seem impossible at first glance, let's talk about Olber's paradox.
Right.
You know how on a clear night, the sky is mostly dark?
Yeah.
That simple fact actually hints at a universe that hasn't existed forever.
Wait, really?
Yeah.
How does darkness point to a beginning?
So imagine if the universe were infinite and unchanging, filled with stars in every direction, right?
Mm-hmm.
If you looked at any point in the night sky, your line of sight would eventually hit a star.
Yeah.
The entire night sky should be as bright as the sun.
Oh.
But it's not, and that's the paradox.
Right.
It suggests that the stars haven't been shining forever,
Okay.
which hints at a starting point.
That's amazing. So this seemingly simple observation about the darkness of the night sky actually tells us something really profound
Totally.
about the universe's age.
Exactly. Now, when it comes to the question of a beginning, Hawking explores arguments from different perspectives, right? So we have religious beliefs, of course, with the concept of divine creation.
Sure.
But he also delves into the ideas of philosophers, like St. Augustine.
St. Augustine. What did he have to say about the universe?
Well, he pointed out that civilization progresses over time, right?
Okay.
We remember who did what, who invented what.
Mm-hmm.
So his argument was, if humanity, and by extension the universe, had always existed, wouldn't we have reached some sort of ultimate level of advancement by now?
Right.
Wouldn't all knowledge already be discovered?
So if the universe has always been here, we should be at some kind of endpoint.
Exactly.
But clearly that's not the case, right? There's always more to learn, new discoveries waiting to be made.
Yeah.
It's a compelling argument, I think.
Yeah, it is. But then we have Immanuel Kant, another philosopher.
Okay.
And he actually proposed equally strong arguments for both a beginning and an eternal universe.
Really?
He called them antinomies.
Okay.
Essentially contradictions that couldn't be resolved.
So we have two completely opposite ideas, both seemingly valid.
Right.
How did he try to reconcile that?
Well, he said if the universe had no beginning, there would be an infinite amount of time that would have to pass before any event, which seemed absurd to him.
I see, yeah.
But then, if the universe did have a beginning,
Right.
then what existed before that?
Right, what was there?
Why would it choose that specific moment to pop into existence?
Yeah.
He was really struggling with the very nature of time, you know?
Yeah.
Yeah.
I see the dilemma. Both scenarios seem to lead to a similar problem.
They do.
Where's the flaw in his reasoning?
So Kant assumed that time existed independently of the universe as something that just was. But what if time itself began with the universe?
Okay.
That's a really radical shift in perspective.
Yeah.
But it's a consequence of Einstein's theory of relativity.
Okay, now my mind is officially starting to bend a little bit.
Yeah.
Time as we know it didn't exist before the universe.
Exactly. It's a really wild concept to wrap your head around.
It is.
And it opens up a whole new way of thinking about the universe's origins.
Yeah.
But before we get too deep into all of that, let's talk about us humans for a second.
Okay.
Where do we fit into this grand cosmic scheme?
Right. Hawking had some fascinating thoughts about human intelligence and its connection to the universe.
Oh, yeah, he did.
In general.
Yeah, he suggested that our ability to reason and to understand the world around us might be a direct result of natural selection.
Okay.
Think about early humans.
Yeah.
Those who could accurately interpret their surroundings,
right.
predict danger, and find resources, those were the ones who were more likely to survive and pass on their genes, right?
So our intelligence evolved because it gave us an advantage in survival.
Mm-hmm.
But here's a question. Does that still hold true today?
Right.
Will our big brains continue to be an asset in the future, especially with all the challenges we face as a species?
That's a question that Hawking leaves open, Our drive to understand the universe might have been very advantageous in the past, but what about now? Could our own intelligence lead to our downfall?
It's a thought-provoking question.
It is.
But for now, let's shift gears and tackle the behemoth in the room.
Yeah.
Einstein's theory of relativity.
Okay.
I have a feeling this is where our understanding of time really starts to get warped.
Yeah, you're not wrong. Before Einstein, physicists thought that time was absolute, like a universal clock ticking away at the same rate for everyone, everywhere.
Right.
But Einstein showed that that's not the case at all.
Oh.
Time is relative. It can be affected by gravity and speed.
Okay, I'm already feeling a little lost. Can you give us an example, something we can relate to here on Earth?
Sure. So imagine two people,
Okay.
one standing still and another zooming by in a spaceship at nearly the speed of light.
All right.
Now, let's say they both measure the time it takes for a beam of light to travel a certain distance.
Okay.
According to Einstein, they would actually measure different times.
Wait, what? But the speed of light is constant, right?
It is, but because the person in the spaceship is moving, their perception of distance and time is altered compared to the person standing still. And that's the really mind-blowing part of relativity. Time is flexible. It's not fixed.
Right.
It's not a universal constant.
So this isn't just a theoretical concept, is it?
Yeah.
I remember learning about relativity affecting things like GPS satellites.
Oh, absolutely. GPS relies on incredibly precise time measurements.
Right.
If we didn't factor in the effects of relativity, both the speed of the satellites and the Earth's gravity, GPS systems would be wildly inaccurate.
Wow. So relativity isn't just for physicists. It has real-world consequences that affect our everyday lives.
Exactly. And Einstein's ideas also really revolutionized our understanding of the universe's evolution.
Okay.
Which leads us to the concept of an expanding universe with multiple possible outcomes.
Okay.
But that's a story for part 2 of our deep dive.
Right. I can't wait. All right, back for more cosmic exploration. Last we left off, we were dealing with Einstein's theory of relativity.
We were indeed.
And the idea that time is not as fixed as we once thought.
Just the tip of the iceberg. From here, we go even deeper into the realm of quantum mechanics.
Okay.
A theory that governs the behavior of particles at the smallest scales imaginable.
So think atoms and all the strange stuff that goes on inside them.
Oh, exactly.
All right, I'm ready to dive into the quantum realm.
Right.
Fair warning, though. My brain might need a backup generator after this.
Don't worry, we'll navigate this together.
Okay.
Now, one of the most important concepts in quantum mechanics is the uncertainty principle.
Okay.
It basically says that you can't know both the position and the velocity of a particle with perfect accuracy at the same time. The more precisely you measure one, the less you know about the other.
So it's not just a limit of our measuring tools.
Right.
It's like a fundamental rule of the universe.
It's built into the very fabric of reality at that level.
That's wild.
And this concept of inherent uncertainty really bothered Einstein.
Oh, yeah. He did not like that.
If you recall his famous line, God does not play dice.
He did not like the idea of randomness in the universe at all.
Not at all.
But if quantum mechanics is so counterintuitive, why do we believe it?
Because it works. It explains phenomena that classical physics just can't. Okay.
Plus, think about all the technology that it underpins. Transistors, lasers, even medical imaging.
Right.
It might be weird, but we can't deny its impact.
So even if it's strange, it's undeniably successful.
It is.
Now let's go back to atoms for a moment.
Okay.
I vaguely remember something from high school
Yeah.
about electrons orbiting the nucleus like a miniature solar system.
Right.
Does that still hold up in the quantum world?
That idea of neat little orbits isn't quite accurate.
Okay.
Think about it. In classical physics, if an electron were orbiting the nucleus like a planet, it would constantly lose energy and spiral inward, eventually crashing into the nucleus.
Sounds like a recipe for disaster.
The atom would collapse.
That can't be right.
Of course not. This is where quantum mechanics steps in.
Okay.
Instead of fixed orbits, electrons exist in energy levels, or orbitals.
Okay.
These are regions around the nucleus where an electron is most likely to be found.
So not like a tiny solar system with electrons on set paths. Not quite. Imagine a musical instrument.
Okay.
You can only play certain notes on a violin or piano, right?
Right.
Those notes correspond to specific frequencies, specific energies. Electrons in an atom are kind of similar.
Okay.
They can only exist at certain energy levels, like specific notes on a musical scale.
That analogy really clarifies things.
Good.
So electrons are like notes on a cosmic scale.
Yeah. It's a great way to visualize it.
I love that.
And just like different notes create a melody.
Yeah.
Those specific energy levels of electrons give rise to the incredible diversity of elements and chemical reactions that make up the world around us.
Now, inside these atoms, we find those elementary particles.
Yes.
The building blocks of matter. Earlier, we briefly talked about quarks.
Right.
They make up protons and neutrons, right?
That's right. They come in different types or flavors like up, down, strange, charm, top, and bottom.
Okay, so a whole zoo of quarks out there.
It is quite a collection.
But what holds these quarks and ultimately everything else together?
Right.
We've got to talk about those fundamental forces.
We do.
I'm with you on gravity.
Okay.
Keeps me firmly planted on Earth.
It does.
Electromagnetism is all about electricity and magnets, right?
That's right.
But those other two, the weak and strong forces, those are a bit fuzzy for me.
So the strong force is the strongest of the four.
Okay.
But it only operates over very, very short distances.
Okay.
Mainly within the nucleus of an atom.
Okay.
It's what binds those quarks together to form protons and neutrons. And it also holds the protons and neutrons themselves together within the nucleus.
So super strong.
Very strong.
But short range.
Exactly.
Got it. Now, what about the weak force? What's its role?
The weak force, while weaker than the strong force, is still much stronger than gravity at these tiny distances.
Okay.
It's responsible for certain types of radioactive decay.
Okay.
Which is basically the transformation of one type of particle into another.
So it's a force of change, of transformation.
It is, very much so.
Interesting. We also talked about the spin of particles.
Right.
That's more than just them spinning around, isn't it?
Yeah, you're picking up on the nuances. Spin in quantum mechanics is a bit more abstract than the everyday spinning we're used to.
Okay.
It's an intrinsic property of particles, like mass or charge.
So more like a fundamental characteristic they just have.
Exactly. And particles can have different spin values.
Okay.
Matter particles like electrons and quarks have a spin of 12.
Okay.
Force-carrying particles like photons for electromagnetism or gluons for the strong force have spin of 1 or 2.
So spin helps determine whether a particle is a building block of matter or a carrier of force.
Exactly.
I'm starting to see how these pieces fit together.
That's the beauty of physics. Speaking of fitting things together, there's another crucial concept related to spin, Pauli's exclusion principle.
Right.
It states that two identical matter particles can't occupy the same quantum state at the same time. They can't have the same position and velocity simultaneously.
So, like, they need their own personal space.
In a way, yeah.
Why is this principle so important?
Well, imagine if it didn't exist.
Okay.
All those matter particles would be able to clump together in the same state, collapsing into a super dense mess.
Oh.
But the exclusion principle prevents that.
Okay.
It gives atoms their structure and prevents them from imploding.
So Pauli's exclusion principle,
Yeah.
the cosmic bouncer, keeping everything in its rightful place.
I like that, yeah.
It's amazing how these abstract quantum rules shape the structure of the universe.
It is.
But physicists are always looking for ways to simplify things, right?
They are, always searching for elegance and unity.
What about those fundamental forces?
Yes.
Are they truly separate, or could they be different aspects of a single unified force?
That's a question that's driven physics for decades.
Yeah.
The quest for unification is a major theme.
Okay.
We've already achieved one significant milestone. with the unification of the electromagnetic and weak forces into what we call the electroweak force.
So two forces became one. That's impressive.
It was a major breakthrough.
What about the strong force in gravity? Are they invited to this unification party?
That's where things get trickier. Theories called Grand Unified Theories, or GUTs, attempt to bring the strong force into the mix, but they're still being developed, and they haven't been experimentally confirmed.
So a work in progress?
Very much so.
What about gravity? The big kahuna of forces.
Yes.
Any chance of bringing it into the fold?
That is the holy grail of modern physics. A theory of everything that unifies all four fundamental forces.
Wow.
String theory is one candidate.
Right.
But it's incredibly complex and not without its challenges.
String theory. Yeah, that one's definitely a brain bender. Perhaps another deep dive for another day.
Perhaps.
But for now, I think we need a change of pace.
Okay.
Let's talk about something a little more, dense.
I believe you're leading us towards black holes.
You got it. Those enigmatic cosmic beasts that seem to defy the laws of physics as we know them.
All right, let's dive in.
I'm ready to fall into this rabbit hole.
Okay, well, before we get lost in the abyss, let's define what a black hole actually is. It's a region of space-time where gravity is so intense that nothing, not even light, can escape.
So a cosmic vacuum cleaner sucking up everything that gets too close.
You could say that.
Sounds a bit terrifying.
They are intense objects, for sure. At the heart of a black hole lies a singularity, much like the one we discussed at the very beginning of the universe. But surrounding the singularity is a boundary called the event horizon.
The event horizon. It has a rather ominous ring to it.
It does, and for good reason. Once you cross the event horizon, there's no turning back. You're forever trapped within the black hole's gravitational pull.
Officially adding avoid black holes to my bucket list.
Probably wise.
But wait a minute. I remember hearing that black holes aren't entirely black.
That's right.
That they actually emit some kind of radiation.
They do.
How is that possible? I thought nothing could escape a black hole.
It is a mind-bending concept. This is where Hawking made a truly groundbreaking discovery. He found that black holes actually emit radiation due to quantum effects near the event horizon. It's called Hawking radiation.
But how does that even work?
So it's complex, but let's try and simplify it a bit. Remember those virtual particle pairs that are constantly popping in and out of existence?
The ones Einstein wasn't too fond of.
Exactly. Now imagine a virtual particle pair popping into existence near the event horizon of a black hole. One particle falls into the black hole while the other escapes.
But wouldn't they usually annihilate each other?
Normally, yes. But the extreme gravity near the black hole can give the escaping particle enough energy to become a real particle, while its partner falls into the abyss. To an outside observer, it appears as if the black hole is emitting particles.
So black holes are slowly leaking energy and mass through this process.
Precisely. This means black holes are not eternal. They slowly evaporate over vast stretches of time.
That's amazing. Black holes aren't entirely black, and they eventually disappear.
That's the remarkable implication of Hawking radiation.
My universe just got a little less scary and a lot more intriguing.
Good. I'm glad to hear that.
Now, this brings us back to the concept of entropy.
Yes.
Remember, entropy is a measure of disorder in a system.
That's right.
Like my desk after a particularly busy day.
Exactly. The second law of thermodynamics states that entropy always increases in a closed system. Things naturally tend towards disorder over time.
But how does this relate to black holes?
Well, at first glance, black holes seem to violate the second law. If you throw something with high entropy, like a box of gas molecules, into a black hole, the entropy outside the black hole seems to decrease. Where does all that disorder go?
It does seem like it just vanishes.
This was a puzzle for physicists for a while. But Hawking's discovery of black hole radiation offered a solution. He proposed that the entropy of a black hole is proportional to the area of its event horizon.
So the bigger the black hole, the more entropy it has.
Precisely. When something falls into a black hole, its event horizon grows. So the total entropy of the system still increases, even though the object itself is gone.
So Hawking radiation saves the day for the laws of physics.
It does appear that way.
But now we've got to address the elephant in the room, or maybe the time traveler in the DeLorean.
Time travel. Yes, time travel.
Did Hawking delve into this at all?
He did. It's one of the most captivating aspects of his work.
Yeah.
You see, certain solutions to Einstein's equations of general relativity actually allow for the possibility of time travel.
Wow, time travel. Suddenly all those sci-fi movies seem a little less far-fetched.
Perhaps, but hold on.
Okay.
The types of space-times that theoretically permit time travel, things like rotating black holes or hypothetical cosmic strings,
Right.
are incredibly extreme. They may not even exist in reality.
So time travel is possible in theory, but in practice, not so much.
That's the current thinking.
Okay.
And there's another idea to consider, the chronology protection conjecture.
Chronology protection. That sounds pretty serious.
It is. This conjecture suggests that the laws of physics might somehow prevent large-scale time travel, like us hopping into a time machine and zipping around the past.
Okay.
It's all about avoiding those mind-boggling paradoxes.
Right, paradoxes. Like going back in time and accidentally preventing your own birth.
Exactly. The classic grandfather paradox.
Yeah.
If you could change the past, you could create all sorts of logical contradictions.
Right.
It would really wreak havoc on the fabric of reality.
Okay, so maybe time travel is more trouble than it's worth?
Potentially.
But what about those theoretical shortcuts through space-time?
Yeah.
Those wormholes?
Yes.
Are those a possible route for time travel?
Wormholes are another fascinating possibility.
Okay.
But they're still very much theoretical.
Okay.
They would require something called negative energy density.
Negative energy density. Sounds even weirder than virtual particles.
It is a strange concept.
Yeah.
But we do have some evidence for negative energy density.
Really?
In the form of the Casimir effect.
Okay.
Remember those two metal plates we discussed earlier?
Oh, right.
It's the ones that get pushed together by a virtual particle.
Right. It seemed like they were attracted to each other out of nowhere.
That's the Casimir effect.
Yeah.
It demonstrates that negative energy density can exist, at least on a very small scale.
Hey.
Whether we could ever harness it to create wormholes or time machines, well, that's a question for the future.
Okay, so my brain is officially in overdrive. We've covered so much ground, from the weirdness of quantum mechanics to the mysteries of black holes and the tantalizing possibilities of time travel.
Absolutely.
But there's still so much more to explore in Hawking's universe.
Oh, there is.
What did you say?
Absolutely. There are those mind-blowing questions about our place in the universe and the very nature of reality itself.
Yeah.
Those are topics we'll delve into when we return for the final part of our deep dive.
Welcome back to the final part of our deep dive into Stephen Hawking's A Brief History of Time. We've explored some pretty mind-bending concepts.
Yes.
From the nature of time to the mysteries of black holes. Now, let's turn our attention to the big picture, our place in this vast and ever-expanding universe.
This is where we delve into the anthropic principle, a fascinating idea that grapples with the apparent fine-tuning of the universe for life.
Fine-tuning for life.
Yeah, it suggests that the universe we observe must be compatible with our existence as observers.
So it's not just about humans specifically, but about the conditions necessary for any kind of intelligent life to emerge.
Exactly.
That's a pretty profound thought.
It is. And there are actually two versions of this principle: the weak and the strong anthropic principle. The weak one simply states that the universe's properties must be consistent with the existence of observers like us. If things were drastically different, we wouldn't be here to ponder these questions.
That makes sense. If the laws of physics were incompatible with life, we wouldn't be having this conversation right now.
Exactly.
What about the strong anthropic principle? How does that differ?
The strong anthropic principle takes it a step further. It suggests that the universe must have properties that allow for life, implying a kind of purpose or design behind its existence.
So the weak anthropic principle is about observation.
Yes.
While the strong one delves into the why behind it all.
You could say that.
Okay, that definitely adds another layer of complexity.
It does.
Are there any specific examples of this fine-tuning?
Oh, absolutely.
That led physicists to even consider these principles?
One of the most striking examples is the incredibly precise values of fundamental constants in physics. These are numbers like the speed of light or the gravitational constant.
Right, constants are, well, constant. They're just built into the fabric of the universe.
Right.
What's so special about them?
Well, the thing is, if these constants were even slightly different, the universe would be a vastly different place. Likely inhospitable to life as we know it.
Oh, wow.
For instance, if the strong nuclear force were just a bit weaker, stars wouldn't be able to form. Or if the electromagnetic force were slightly stronger, atoms wouldn't hold together.
Wow, so those seemingly random numbers are actually crucial for the universe as we know it.
They are.
It does make you wonder why they have those specific values.
Exactly. It's as if the universe were carefully calibrated to allow for the formation of stars, planets, and ultimately life itself.
So does this mean the strong anthropic principle is the answer then?
Well,
was the universe designed with life in mind?
That's the million-dollar question.
Yeah.
And the anthropic principle doesn't offer a definitive answer. Some people see it as evidence for a divine creator, a guiding hand behind the universe's formation.
Right.
Others propose alternative explanations like the existence of a multiverse.
A multiverse, as in an infinite number of universes, each with its own set of physical laws.
Exactly.
Now that's a mind-blowing concept.
It is.
So it's either a grand design or a cosmic lottery. Both possibilities are pretty incredible to contemplate.
They are.
Now before we wrap up our exploration of Hawking's universe, I think we should touch on one more fascinating concept.
Okay.
String theory.
Ah, yes, string theory.
It's been lurking in the background of our conversation.
It has.
And I'm ready for a final dose of mind-bending physics.
All right, let's dive in. String theory is a very ambitious attempt to create a theory of everything.
Okay.
A framework that unifies all four fundamental forces of nature.
Okay.
Gravity, electromagnetism, the weak force, and the strong force into a single elegant theory.
It's the holy grail of physics, isn't it? To find one equation that explains everything.
It is a grand ambition.
Yeah.
The basic idea of string theory is that the fundamental building blocks of the universe are not point-like particles, as we've been discussing, but tiny one-dimensional strings.
So instead of tiny dots, we have tiny vibrating strings.
Precisely. And the different vibrations of these strings give rise to the different particles and forces we observe. Imagine a violin string. It can produce a wide range of notes depending on how it vibrates.
Right.
Similarly, in string theory, those tiny strings vibrating at different frequencies create the incredible diversity of particles and forces that make up our universe.
I love that analogy. It makes this abstract concept a bit easier to grasp.
Glad to hear it.
But how can we test this theory?
That's one of the major challenges.
Yeah.
Those strings are thought to be so incredibly tiny.
Right.
Far beyond the reach of our current experimental capabilities. So for now, string theory remains a compelling theoretical framework, but one that's difficult to prove or disprove experimentally.
So a beautiful idea, but one that's still shrouded in mystery.
Yeah.
It seems kind of fitting, doesn't it? Our journey through Hawking's work has been filled with mysteries.
It has.
From the beginning of the universe to the nature of black holes.
Hawking's work wasn't just about finding answers. It was about embracing the unknown, asking the big questions, and constantly seeking a deeper understanding of the universe and our place within it.
He also delved into the philosophical implications of a universe governed by scientific laws.
He did.
What did he conclude about the role of a creator in a seemingly random and uncertain world?
He acknowledged that the randomness and uncertainty we encounter in quantum mechanics could be interpreted as evidence of divine intervention, but without purpose or direction. He saw the goal of science as understanding the probabilistic nature of reality, not predicting events with absolute certainty.
So, accepting that we may never have all the answers, embracing the mystery, that's a humbling perspective. And it reminds me of his no-boundary proposal. This idea that the universe is finite, but without boundaries or singularities.
Right. That proposal eliminates the need for a beginning or a creator in the traditional sense. It suggests a universe that is complete and self-contained. Existing without the need for something to set it in motion.
Wow. A universe existing purely by its own rules, without the need for a beginning or an end. That's a profound concept. It seems our deep dive has left us with even more questions than answers.
It often does.
But I wouldn't have it any other way.
Me neither. That's the beauty of exploring these big ideas. They challenge our assumptions, expand our understanding, and leave us with a sense of wonder and awe.
And that is a perfect note to end on. To all our listeners, we hope this deep dive at Stephen Hawking's universe has sparked your own curiosity and left you pondering the mysteries of the cosmos. If you have more brain-tickling questions or topics you'd like us to explore, don't hesitate to send them our way. We're always up for a challenge. Until next time, keep looking up and keep those minds buzzing.
Did you get any of that?